Okay, so here in lesson 32, we're going to start looking at curve sketching. And you might say, well, we've been doing stuff with graphs a lot already. And you're right, we've been finding different features of graphs. But the idea behind doing this is a couple of things. First of all, yes, I know if you punch a function into your calculator, it'll show you what it looks like. But what it won't do is actually tell you what all these features are. Okay? If you want to then analyze that graph, it's one thing to know what it looks like, but it's another thing to know, hey, this is exactly where the max is, or this is exactly where concavity changes, and things like that. The other thing that is helpful as we're doing this is to realize that once you learn how to do it, it's actually sometimes faster to do this by hand than even to use your calculator. Okay, and hopefully you guys will see that as we go here. All right, so let's take a look at some of the stuff that we're able to find, and here's where we're really going to be incorporating a lot of what you did with pre-calc honors, dealing with rational functions, and then we're going to pile onto it all the stuff that we've learned with derivatives to be able to get a really, really thorough picture of what's going on with a rational function, okay? So here are some guidelines. First of all, determine domain and range. Now, the domain you definitely can get right at the beginning. The range you may have to wait until you find your max and min points and your horizontal asymptotes and other stuff. So that may kind of evolve as you figure out other things. All right, so you definitely want to, though, give the domain and range. You want to find all the intercepts, x and y intercepts, asymptotes, and identify symmetry, okay? Is there symmetry in this graph? And then finally, notice the first two involve no calculus. All right, that's all stuff that you used to do. Now, we're also going to use the first and second derivative to find extrema, points of inflection, intervals of concavity, intervals of increasing and decreasing, and all of that stuff, okay? So let's actually use this function here as our first example. We have 2 times the quantity x squared minus 9 over x squared minus 4, okay? So, let's start with our domain. What's the domain?
X cannot be equal plus or negative 2.
Yeah, there we go. X cannot be plus or minus 2, because that'll make the derivative equal to 0. Or the denominator equal to 0. Wrong D word. The denominator equal to 0. Okay? Now, here's a question that we had to ask ourselves before, and we should now too.
Range?
Are those values giving us holes or asymptotes? How do we know?
Because the function is going to be undefined.
Because it's not 0 over 0.
It's not.
It would be 2 times.
Something. Yeah. Yeah, it's not a hole. It's not something that will cancel out. And you could even factor, because we'll use that again in a sec, x plus 3, x minus 3 on the top, and we've got an x plus 2, x minus 2 on the bottom. Okay? So these are vertical asymptotes, which actually we have listed down here. Okay, so x equals 2 and x equals negative 2. All right? Now, what else can we figure out pretty easily just by looking at the function here?
Y-intercept?
Okay, y-intercept is a point 0 something, right?
Yeah.
So if you plug in 0 for x, what do you get?
So negative 18.
Negative 18 over negative 4, so positive 9 over 2, which is 4.5. There you go. So we got a point there.
Y x-intercepts,
Okay, x-intercepts.
3 and -3.
Yes, okay, the x-intercepts are where the whole function equals 0, so you look at the numerator, and we've got 3, 0, and -3, 0, okay? So we're just finding as much stuff as we can. We haven't even done any calculus yet. Alright? And then, yeah, here's what we were talking about yesterday. We can get horizontal asymptotes. What is the horizontal asymptote here?
Boba bottom.
Boba Bottom tells us it's y equals 2. By the way, guys, when you are asked to give a horizontal asymptote or a vertical asymptote, please remember those are lines. Don't just write down 2. It's a line, y equals 2. So at this point, I want to stop, because at this point we basically, short of just plugging in random numbers for x and getting points, we figured out everything we can without using calculus. And what I would recommend here is that we actually sketch what we know so far. Okay? Oh, that's terrible. Let's try that again. There we go. Okay, so I have asymptotes at x equals 2. I have x equals -2. So there's another asymptote.
How is it bigger on top? Where is it?
They're actually equal because they're both x squared, so
Yeah.
it's 2 over 1.
So how is it? So they're equal?
The right
The coefficient, they are bigger on top?
Bigger on top, there's no horizontal asymptote. Bigger on bottom, it's y equals 0. Okay? So here it was y equals 2. Okay? So we have this horizontal asymptote. And then we have a few points that we know so far. We have an x-intercept at 3, 0. We have an x-intercept at -3, 0. And we have a y-intercept at, there's 4, 5, so there's 4.5. I have to draw this a little taller. Okay?
Cool question.
Yes.
Isn't that a graph?
Yeah. So ours should look like that, right? When we're done. Okay, so let's now think about actually one other thing. I'll write this down here. X does not equal plus or minus 2. There is something here about symmetry. Is there going to be any symmetry in this graph based on the equals, based on the equation?
Yes.
How?
What?
What kind of symmetry?
They'd be an axis.
Okay, there's symmetry across y. Actually not across x.
No, like, isn't it gonna go this way on the left and the right?
Yeah, but
It will, but that's not symmetry across the x-axis. That's actually symmetry across the y, because the left and the right sides will be mirror images of each other.
Oh, okay.
Now, how do we know that that symmetry is going to exist here?
because both top and bottom are to the power of 2.
Okay, if I plug in a negative x, remember this is how we test for an even function. This is actually an even function because if I plug a negative in for x, I end up squaring it in both cases and it looks exactly like f of x. Alright, so the symmetry here, we can tell f of negative x gives us the same thing as f of x. So that's an even function, and an even function has symmetry across the y-axis.
So if it was negative f of x equals f of x, would that be symmetric across the x-axis?
That's symmetric across the x-axis, which in that case it wouldn't be a function, right?
Yeah.
So That's a nice thing. We don't need to worry about across the x-axis if we know it's a function.
How, like, it has a symmetry across the axis.
It would be some other relation, like the ones we were doing when we did related rates or implicit differentiation. You know, we had circles or ellipses and those kinds of things. But we're not going to have those here. Okay? The other type of symmetry that you have is symmetry about the origin. And that's when you rotate the whole thing around the origin 180 degrees. It looks identical to itself. And that's if you plug in a negative for x and a negative for the y and simplify, and it comes out to f of x. Okay? So, alright, so now it's time to do some calculus here. Alright, let's actually do some calculus.
What, can we do it through the limits and the, what's it called? Low something here?
L'Hopital's rule?
No.
Well, we need to find features of a graph, so we're going to do derivatives here. And we're going to find max and min points or plateau points if there happen to be any. And then we're going to find points of inflection as well. So let's check this out here. First of all, by finding f prime of x. What do we need to use to find f prime of x?
Quotient rule?
Yeah, quotient rule. Okay. So I have 2 times the derivative of x squared minus 9, so that's 4x, times the bottom, minus the top, which is 2 times x squared minus 9 times the derivative of the bottom, which is 2x. So that's going to be a 4x x squared minus 9 all over x squared minus 4 squared. Okay? Now, let's simplify a bit, and then we can start using that first derivative. Alright, so I'm going to have a 4x cubed minus a 4x cubed. So that's really nice. That cancels out. And I have a minus 16x plus 36x. So that gives me a 20x on the top over x squared minus 4 squared. Okay? So at this point, I can find critical numbers by setting this derivative equal to 0 or seeing where it's undefined. Okay? So where does this equal 0?
0 or plus only 0.
It equals 0 there, but also, what?
Or 2. Square.
It's undefined, it's x squared minus 4 squared.
So
It's undefined at x is plus or minus 2.
And it's also going to be a critical point.
Now, are all those critical points?
No.
Yeah.
Yes.
No, because x can't equal plus or minus 2.
Aha. This is why we want our domain first, right?
Oh.
Our domain said x could not be plus or minus 2. So, yes, the derivative is undefined there because the whole function is undefined there. Okay? So, when I'm listing out critical numbers, the only critical number I'm going to get is x
0.
equals 0. And that means that my y-intercept happens to be a critical point, and the only critical point that we've got.
Right.
Okay? So 0, 4.5 is a critical point. Now, this is something that I told you was coming up, and now we're going to see it here, okay? We have to do a sign diagram to determine what we've got and what the direction is here, okay?
Yeah.
So we've got this, and I'm going to put the critical number on here, but I do also put any discontinuities. I also put the 2 and the negative 2 here. And this is why, okay? Even though it's not an actual critical point on the graph, those discontinuities can impact the direction or concavity or whatnot of our function, okay? So here we're looking at first derivative, so we're talking about direction. And if we were to plug in a negative number, we'd have 20 times a negative over something squared, which is always positive. So it's going to be negative. And the thing is, we're going to get the same thing if we plug in something between -2 and 0. If I plug in a positive one, I'm going to get 20 times a positive over positive in both of these areas. Okay? So what we see here is decreasing, decreasing, increasing, increasing.
We have two plateau points and one relative minimum.
You're right, we have one relative min, and we're tempted to say that those are plateaus, but then we remember that those are asymptotes, okay? So, at this point, guys, we actually have a really good idea of what this thing looks like, okay? Because this right here is a relative min. And if I come over here to what I've already drawn, I can see, all right, it's decreasing as I go from -infinity up to -2. What's it doing as it's approaching -infinity? As we go to the left,
Oh, it's approaching line as well.
it's approaching this horizontal asymptote, right? So, notice, I know I'm hitting this point. It's going to approach the asymptote, but as I go from left to right, it's decreasing all the way as it approaches this -2. And the reason why it continues to decrease after -2 is because it goes to -infinity on the left, then it jumps way up here to positive infinity and comes down until we hit the min. Then it goes all the way back up as we approach the vertical asymptote there.
How do you know the min is?
I know the min's there because I did my sign diagram.
And then
No,
you plug
you know
in
the
0
number.
back here.
Oh, that was my y-intercept. We found that point when we found the y-intercept, 0, 4.5. Okay? So I hit the asymptote, it jumps down to -infinity, it comes up, hits that x-intercept, and then as we go to positive infinity, it's approaching that horizontal asymptote again. Okay?
We had that on the top. We had a graph like that.
We've seen graphs like this before, yeah. We just haven't found all the features of them. Okay?
So do we still need to find the second derivative?
So, well, what we want to do at this point with second derivative, in this case we can kind of just look at it and we know what the concavity is.
Yeah.
We know it should be concave down from -infinity to -2 and from 2 to infinity. And it should be concave up between -2 and 2. Alright? There are no actual points of inflection in this case. Alright? Now we can prove that
My findings and derivative.
by going ahead and finding the second derivative.
Wait, would the point of inflection be the isotope?
Well, an asymptote isn't
Yeah.
a point, so it is a place where concavity changes, but it's not an inflection point. Alright, so here's second derivative. Let's do this one real quick here. F double prime of x is 20 times the denominator minus the numerator times the derivative of the denominator. So that's going to be actually 80 x squared times x squared minus 4 to the first power. 20x times the 2 times the 2x is 80x squared. Yep. And then that's all over an x squared minus 4 squared squared. So now it's to the fourth power. Notice both parts of the numerator have an x squared minus 4 in them. So I'm going to cancel those out with one of the ones on the bottom. Check this out here. So this right there, that right there will cancel out one of these four. Rather than rewriting the whole thing, it's a common factor on the top. So I canceled it out. So now I simplify the numerator, and I get the second derivative equal to 20x squared minus 80x squared is a negative 60x squared minus 80
You can factor 20 out.
all over an x squared minus 4 to the third power. We could factor out a minus 20 if we want. Okay? Yeah. Now, if we were to do this, if we were to try to find, let's say we hadn't been sketching along the way, and we were trying to find where this equaled 0, we'd set the numerator equal to 0. So if I factor out a negative 20,
Wait, it's going to be undefined.
okay, if I plug out a negative 20, I've got a 3x squared plus 4. Will that ever equal 0? No. That'll never equal 0. So notice I have no critical numbers. This gives me the x plus or minus 2 again, but x can't be that either. So we just proved that there are no points of inflection on this graph. If I plug anything into my function, I'm going to get, well, if I were doing a sine diagram, I would put those asymptotes on there again, but that's all that would be there. Negative 2 and 2. My second derivative is negative to the left. If I plug in a 0, I get a positive. And if I plug in something bigger than 2, it's negative. So I know I'm concave down, I'm concave up in the middle, and then I'm concave down. And that matches what we thought just by looking. Okay?
Does that show that we don't need a point of inflection to change concavity?
Yeah. Even though we don't have a point of inflection, we do still have concavity. It still is there.
Maybe we should change concavity.
The only thing that's changing it are those asymptotes. Okay? Now, if it's helpful for you to go ahead and do different intervals, okay, and make a table like this, then by all means do it, okay? Here we have the function, the first derivative, the second derivative, okay?
So that test intervals part is kind of like optional, like it's not, the rest like.
The idea of that is to, I mean, you're going to do it regardless
Yeah,
to
but-
answer a question. It's a matter of how you organize it, okay? Basically, all here, this is a vertical asymptote. Okay, that's a vertical asymptote there, and it's a vertical asymptote at 2. Okay? Now, these different intervals, as we're looking at, are two different sine diagrams. From negative infinity up to negative 2, our function is, our derivative is negative, or wait, wrong one. Our derivative is negative, so our function is decreasing, okay? Our second derivative is also negative, so it's decreasing and it's concave down, okay? From negative 2 to 0, this is negative, but the second derivative is positive, so it's decreasing, but it's concave up. The first derivative equals 0 here. The second derivative, notice, is positive. When the first derivative was 0 and the second derivative was positive, what do we have? No, we have a min. Yeah, the second derivative test. So here the second derivative confirms what we saw on our sine diagram of the first derivative.
Yeah, so it's concave up, so we have a min.
Yeah, so we've got a min. A relative min. Okay? From 0 to 2, both the first and second derivatives are positive. So now we're increasing and it's still concave up. But then from 2 to infinity, the first derivative is positive, second derivative is negative. So it's increasing, but it's concave down. Okay? So that's a table that could, if that's helpful for you, you could make a little table like that and use it to interpret things. I personally just usually use the sign diagrams, but some people like the tables. Okay? It's totally up to you. That's a lot of work for one graph. Okay? Obviously, if we weren't stopping along the way to explain everything, we could get it done in a lot faster, but it's still a lot of work for one graph. But what I want you guys to understand is that there is a lot to tell from these graphs. And if this were a model of some kind of different phenomenon, we would be able to tell a lot about its velocity or its acceleration, or when is velocity changing, or where is it at this time, or something like that. We could figure out a lot of different things, and that's why we find all these features. Okay? It's not so that we just have these random graphs we're able to sketch. It's so that if we had a model of something, as you'll see in homework, you guys will have some actual application type of problems to real life situations. You'll be able to then interpret, okay, hey, from 0 to 2, what's happening? Oh, well, the function's increasing, so we must be moving upward, but also the second derivative is positive, so we're moving upward and it's accelerating, so we are speeding up. You know? We have those different kinds of applications. So here on example 2, you can see at the bottom we've got a ton of stuff that we can find for this function. We have the function f of x equals x squared minus 2x plus 4 over x minus 2. And if we're trying to find different features, these are all the different things that we might need to consider. Okay? So to start out with, let's start out with the stuff that we learned how to do a long time ago. Okay? The most basic, let's start with our domain. What's the domain on this graph? Yeah, the domain is all real numbers except for 2. So x does not equal 2, we could say, is our domain. Now, what does that tell us about 2? There's either a hole or a hole is a removable discontinuity, or a non-removable, which is an asymptote. Okay, a vertical asymptote. Which one is this? Yeah, it's a vertical asymptote. The only way it could be a hole is if I could factor the numerator and we could cancel out the x minus 2 here. Okay? Well, if it were x squared minus 4x plus 4, then that would work. But in this case, it doesn't work because the top doesn't factor. Okay?
Also of the C and the sum of the B, right?
Is it a rubber side?
The multiples of the factors of the C and add up to B, yeah. So there's no way that factors. Okay, so we have a vertical asymptote at x equals 2. What other things can we find pretty easily over here?
Horizontal.
Okay, the horizontal asymptote, which in this case,
None.
there are none, yeah, okay.
How would you know that? Oh, no.
Blah, blah, blah.
You do.
Blah, blah, blah.
This is what we learned yesterday, okay, so it's bigger on the top, so there are none.
X-intercept.
X-intercepts, so the x-intercepts are where?
X equals 0. So
Y
No, when.
The x-intercepts are where
Y equals 0.
y is 0, okay? So in this case,
The top is.
Actually,
the top would end up being 0.
Oh, we got.
So x squared minus 2x plus 4 equals 0. How do we solve this? Quadratic formula, okay. 2 plus or minus square root of 4 minus 4 times 1 times 4 all over 2. And what do you see here?
The square root of 0.
Yeah, negative, a square root of a negative here, so
Imaginary.
these are not real,
So we don't include
so we're not going to include them. That means there are no x-intercepts.
Y-intercepts are easy.
Huh. Yeah, now the y-intercept is where x is 0.
-2.
So that's 4 over -2, which is -2. So we now know a point on the graph. 0, -2.
Wait, so values in the Y which X?
Okay. So now we have
How did you find the x-intercept, y-intercept again?
the y-intercepts when x equals 0.
It's
Plug in
the-
0 for x.
Oh,
Just plug in 0 for x. Okay? So we know that, and we have a vertical asymptote at x equals 2, so I'm going to sketch that part so far. Okay? Now, let's talk about end behavior. End behavior. Now, this is something that you guys talked about last year a bit, but not necessarily in a rational function. Okay? Notice in the numerator and the denominator, the leading coefficients are positive. That tells us what's going to happen on the right side. As x goes to positive infinity, the right-hand side is going to positive infinity. Alright, so I know that this is going to look something like this. Maybe not exactly like that, but I'll just draw it for the moment. Okay?
Because it's positive, both values are positive, or just one?
Yeah.
You know that.
And if you think about the top and the bottom, the parabola here on the top looks like this, right? And the line on the bottom looks like this.
So negative infinity goes to infinity still.
So negative infinity goes where?
Negative.
To negative infinity.
Because
Okay?
it's what, positive over a negative?
Yeah, because it'll be a positive over a negative. Okay? So if you think about the pieces here and where they're going, that'll help you figure out, where the whole thing goes. All right? So there's a little bit to help you figure out end behavior. Okay? I know it's going to go down to the left and up to the right. Okay? Now, one other thing here before we actually start doing any calculus, because everything else, actually I should say two different things. One is the symmetry. And remember, if it's going to be symmetrical, it's got to have something where you could plug a negative x in and it'll look exactly the same. And in this case it won't. Or you plug a negative x in and it comes out exactly the opposite. That would be symmetry around the origin. And in this case, it won't do that either. So there's no symmetry here.
Because the bottom is not the same, right?
It's not square.
Yeah, the bottom isn't squared, x isn't squared in these places, and these other constants here make it so that
What should be
you
the
plug in
same?
a negative and it messes the whole thing up.
Y should be the same if you plug in the negative.
If it were symmetrical, it would be the same.
So you would take one x, a positive x, and a negative x, and the y's should be the same or like
Correct.
reciprocal.
Correct.
Negative.
Not reciprocal. If they're the opposites for all of them, then it's symmetrical if you rotated it around the origin 180 degrees. Okay? If it's exactly the same, that means you have symmetry across the y-axis. It's an even function. Okay? Symmetry about the origin is odd function. Symmetry across the y-axis is an even function. Okay? So this isn't either of those. Alright, this is not either of these.
What's the odd is the origin?
Yeah, around the origin. Okay? The last thing that we can do without calculus is finding the other asymptote. And you say, wait, there are no horizontal and we already found the vertical. What other kind of asymptotes are there? The z-axis?
Yeah.
What?
Like y equals x.
There are slant asymptotes, yeah. Now, do you remember how we tell if there is a slant asymptote?
What is this slant asymptote?
Isn't
The degree on the top is bigger,
yes. So you
but
just
not
like-
all the time. It's only when the degree on the top
It's
is
one
bigger, one
and
bigger.
then you
Good,
do
Josh.
synthetic division, right?
Then you do the division, yes, okay? So, check this out here. Let's find the slant asymptote, okay? So I'm gonna take that numerator, okay? And guys, you can do synthetic division or you can do long division. Either way works for you, okay? So I'm gonna do this here. I'll put down the 1, the -2, and the 4. And in the box I'm gonna put a 2 because I'm dividing by x minus 2. And remember, you add straight down. 1 plus 0 is 1.
2,
Then you multiply by 2. You add straight down and get 0.
2.
You multiply by 2, you get 0. You add straight down, you get 4. Okay? Now, if you remember here, this was x squared.
It's gonna be x.
This was x squared, this was x, and this was the number. So down here, this is the x, this is the number, and then this is the remainder.
4 over x minus
It's 4 over x minus 2. Now, when we are finding the slant asymptote, we don't care about the remainder. Okay? We don't care about the remainder. All we look at is the rest of it, and that actually gives us the slant asymptote right there. In this case, it happens to be the line y equals x. Okay?
What is
So
it
just a straight vertical
A slant asymptote is something
line,
that we approach but never cross, but it happens to be on an angle. Okay? Like that. Now, what's going to end up happening at this point, you guys last year would sketch what this looked like. Okay? Really, we haven't done anything that you didn't do last year yet. Okay, so if you're totally lost, we got a little bit of reviewing to do. Okay? We're just got to bring it back to memory, because I'm sure you knew how to do it at some point. Alright, so what we have here is you would sketch something approaching the vertical asymptote, coming down here somewhere, and then approaching that slant asymptote. You'd have the same thing happening here. We'd have going to -infinity, and somewhere in here it would go like that, and it would approach the slant asymptote. Okay? Now, where the calculus comes in is, last year we always were just kind of guessing how far these
So now we can see.
corners actually came in. Now these are going to be the relative max and min points. Okay? So we will be able to find exactly what this ought to look like. Let me get rid of this estimation and we'll get a better job of it here using the derivatives. Okay?
That line is the first derivative on top of the standard slant lines. The line you just approximated, the parabola you just approximated.
That would be the original function.
No,
What I just sketched in green
yes.
is an approximation of what the function is.
So those blue lines are simply, yeah.
Those are just asymptotes.
Yeah.
Okay? So let's take a look at our first derivative. Alright? We need our first derivative. We're going to use quotient rule. F prime of x,
Is 2x
2x minus 2, times x minus 2, minus 1 times x squared minus 2x plus 4 all over x minus 2 squared. We FOIL and simplify. I know you guys know how to do this, so we'll just do it fast. We have a 2x squared minus x squared, which is x squared. We have a minus 6 plus 2, so minus 4x. We have a plus 4 minus 4, so that's 0. That's nice. Alright, so that whole thing simplifies down to this.
And we can factor out.
Okay?
We can factor out x.
Alright, so we could factor out x, and we would do that because we want to find where the derivative equals 0 and where it's undefined in order to determine critical values. Okay? So it equals 0 when x equals what?
X 0 and 4.
0 and 4. It's undefined
2.
at x equals 2. Alright? Now, when we do a sign diagram for this, okay, we need to put these in order 0, 2, and 4. One thing we need to remember, what do we have at 2? An asymptote. So no matter what it looks like, increasing or decreasing, it's not going to be a max or a min or a plateau. That is an asymptote. Okay? So when we do a sign diagram here, if I plug in a negative, no matter what I plug in, the denominator is positive because it's squared. But if I plug in a negative 1, I have negative 1 times negative 5, that's positive. So I know I'm increasing as I approach 0. And then if I plug in a positive 1, I'll have 1 times negative 3, so that's negative. So that's decreasing. So what do I have at 0? I have a relative max. And at this point, guys, I can go ahead and sketch this left-hand side of my graph. This y-intercept that we found before is the max, so I know that it's going to approach the y-intercept or the asymptote there, and it's going to approach the asymptote to the left. So that's what this looks like. Okay?
So x equals 0 is a max.
X equals 0, y equals negative 2 is a relative max point. Yes. Okay? So then I plug in something between 2 and 4, like 3. I have 3 times a negative 1, so that's decreasing. But 2 is not a plateau, it's an asymptote. And at 4, if I plug in something bigger than that, like 5, I'm going to get a positive derivative. So that means 4 is a relative min. Okay? So I come over here, 3, 4. So somewhere around here, I can actually plug in 4 into my original function. And I would get 16 minus 8 plus 4, which is 12, divided by 2, which is 6. So the relative min is the point 4, 6. The relative max was the point 0, negative 2. Okay? And notice here, I'm coming down from positive infinity as I pass this asymptote. And then I'm increasing afterwards and approaching my slant asymptote. Okay, try to draw that a little smoother while still recognizing that as the min point. And there's the other half of my graph. Okay?
Yeah.
Now question, just by looking at it, what's our concavity?
Upwards and downwards and upwards.
Okay,
Down from.
where are our points of inflection?
2.
Two.
There are
There are none.
It's not, it's
2 is where inflection does change, but that's that's a discontinuity.
yeah.
Okay? So let's fill some things in here. The only critical numbers I have are 0 and 4, which gave us our relative max and our relative min.
Isn't 2 a critical number because it's undefined at 2?
Well, but the function is not even defined at 2, so we wouldn't consider that a critical number. If the original function were defined at 2, but the derivative was not, then we would consider it a critical number. Okay? And then possible points of inflection. There actually are none. Now let's just not go by what we can eyeball from the graph. Let's actually do this. If I did the second derivative, f double prime, the derivative of the numerator in this first derivative, I'm going to use this version right here, would be 2x minus 4 times an x minus 2 quantity squared minus the x squared minus 4x times the derivative of x minus 2 squared. So that would be times 2 times x minus 2 times 1, the derivative of the inside. And then that whole thing is over in x minus 2
Wait, what?
to the 4th.
This screen. Let's try this real.
Okay, sorry, I lost the screen there for a sec. X minus 2 to the 4th, because it's squared already, and now we got to square it again. Okay? Now, watch this closely here. Notice both terms in the top, this and this, both have an x minus 2. So I'm going to cancel out this and one of these two with one of these 4. So it's going to be a cube on the top, or on the bottom. And then I'll simplify. Alright? So I took out the common factor of the x minus 2 there, one of the x minus 2's there, and I canceled those with one of the x minus 2's down here. And now it's just a matter of FOIL and simplify. So I'll do that real quick here. 2x squared minus 2x squared is gone. I've got a minus 8 minus 4 is negative 12 plus 8 is a minus 4x. And then I have a plus 8, just a plus 8, yeah. And that's all over x minus 2 cubed. Alright? So check this out. If I keep going, I'm going to factor out a negative 4, and I have an x minus 2 over an x minus 2 cubed. So this whole thing simplifies to negative 4 over x minus 2 squared. Okay? So when will this equal 0? Never. That's why we don't have any points of inflection. And the only time it's undefined is when the original function was undefined as well. So again, we have no points of inflection here. But if we do put that, if we did do a sign diagram, check this out, we would put a 2 here because that's where the function's undefined. And if we tested the second derivative, it would be negative to the left and it would be positive to the right. And that's why we have it concave down to the left of the asymptote, and it's concave up to the right of the asymptote. Okay, so you can still do the sign diagram, you just use discontinuities along with anything that you got to make it
Just
0 or
continuous
undefined.
here because of the bottom, right, of the denominator.
Yes. Joey?
This is probably just like a hole in my algebra knowledge, but if you're setting like x minus 2 quantity squared equal to 0, you could just disregard the squared, right?
Yeah, because if you square root 0, you get 0. Yeah.
I was debating on the top.
All right, now there is a table here that you can use. You can make this little table yourself, okay, if you want. You know, here at x equals 2, this was a vertical asymptote. Okay, this was a vertical asymptote at x equals 2. On the interval from negative infinity up to 0, the first derivative was positive and the second derivative was negative. So that means our function was increasing and concave down. Okay? At 0, the first derivative was 0, and by the way, the second derivative was still negative, which means by second derivative test, it's a max. We showed it was a max with the first derivative test as well. But we have a max, a relative max point here. Okay? On the interval from 0 to 2, the first derivative is negative, second derivative is negative. So it is decreasing and concave down. Okay? Then we have negative positive, which means we're decreasing and concave up. At x equals 4, the derivative was 0. The second derivative was positive, so that means we have a relative min. And then from 4 to infinity, both derivatives are positive, which means we're increasing and concave up. Okay? And now that we see all this, we can actually see the places where it's speeding up or slowing down. Remember we talked about that? If the signs are opposites, it's slowing down. Here the signs are the same, so it's speeding up in a downward direction. Here the signs are opposite, so it's going down, but it's slowing. And then it hits the min, and then it starts going up, and it's speeding up as it goes up because the signs are the same. Okay, so you could tie in things that we've done in the past as well here.